So Deringer-Ney and Deringer-Ney, as we know it today, was the joining about 20 years ago of the Deringer Manufacturing Company and the Ney Company. So Ney was very heavily into precious metal alloy design and electrical contacts, and Deringer Manufacturing very much in power type contact applications. Really the heart of our development process has been focused very much on materials, material R&D, and then the application of those materials. And that's how we get to what we are as a vertically integrated company, where we're making the alloys, we're making strip wire product from the alloys, and then some fabricated components from the alloys. Some of those fabricated components are electrical contact components, and that's kind of where our discussion will be focused on today. We make many different types of configurations of electrical contacts. Represented here are some assemblies that include electrical contacts. As you see here, this is a slip ring assembly that utilizes a cantilever beam contact, standard pin and socket contacts that utilize many different configurations of materials, and then pogo pins, or contacts that are typically used as some spring pin on, say, a flat. And of course, many, many more. This is just scratching the surface, right, of all the different configurations that you can imagine. And so the focus today is going to be on the electrical contact design process, and really focused on the mechanical aspect of how do we approach the electrical contact design process. Obviously, there's many ways that you can go about this, and this is just kind of one perspective, and really meant to generate sort of a conversation with our customers and compatriots. So we start with defining the design envelope. In a lot of ways, this follows what we're now coming to as an industry of following sort of ISO type processes for design and development, right? So we define our design envelope, right? When we're thinking about electrical contacts, one of the things that we think about first is, well, what are the type of uses that we discussed in the design envelope, and now what kind of contact force do we think is needed? Come up with a contact concept. What's the mechanical configuration going to be? How's that fit into the space? What type of material properties are needed? We'll talk a little bit about material properties today, but not go too much in depth. Then model the system. And what do we consider in modeling the system? And then prototyping, where prototyping we won't hit on too much today, right? And then after that, well, do you need to go back, iterate the design based on any shortcomings identified, and then after you iterate and you have something you're happy with, go on to characterization and testing. I won't go too much into testing. Characterization, we'll talk about a little bit. All right, obviously, if you then go back to an iteration cycle, depending on what's needed to improve upon, or you then go on to product launch. So first, defining the design envelope. So general categories, and I won't go too in depth into this, but covering geometrical constraints, electrical conditions, all the mechanical criteria. So we go from geometrical constraints, electrical conditions, all the mechanical criteria, and life and reliability criteria. And really what this starts to build is essentially what we consider the, in an ISO process, or APQP if you're involved with automotive, is like design, all the design criteria. And this starts to build like a DFMEA for the process. And so next, we'll talk a little bit about contact force and just generally what contact forces are selected, and where do you just, what might be a starting point depending on the type of contact you're designing. So at the low end of contact forces, usually these are sliding contacts that have a lot of mileage on them, or a lot of kilometers on them. So hundreds to thousands of kilometers of travel are typically fairly low contact force contacts, because that helps limit the wear. Frequently they're in a sealed environment. Sometimes that sealed environment's hermetically sealed. Sometimes it's just a nominally sealed with in some enclosure. And then frequently, because of the low contact forces, they're redundant contacts. So there's multiple contacts for any given electrical channel. As we move up in the force scale to sort of medium forces, they might be sliding contacts that have, or any contacts that have more debris in the system. So you need some contact force to be able to move that debris out of the contact interface. You may have vibration or acceleration forces that have to be accommodated. Say, automotive applications, right, have a lot of vibration. Drilling, oil and gas type applications. Some satellite applications, and then tarnish. So contact force and tarnish and corrosion products also go together. And then when we look at the high contact forces, typically higher contact forces are power applications. There's arcing forces that have to be considered. Also, certain material systems require higher contact forces. And then if there's no contact movement, maybe on assembly, say a bolted contact assembly, or an assembly that has a very high spring rate, crimped assemblies, and again, bolted assemblies, those might utilize much higher forces. At the low end, this is a figure here that is meant to sort of explain or illustrate reasons for sort of applying minimum contact force criteria. And you'll see contact resistance here on the left versus contact force. And this is for 4 different pure materials. Now you can see differences in material type, particularly nickel, which is an oxide former, has much higher contact resistance than, say, gold, silver, and palladium. But very notably, there's some force that's common between all of them where the contact resistance has a lot less noise. That reduction in contact noise frequently drives minimum contact force for a certain assembly, or the utilization of multiple contacts. On the right here is an example of, again, contact resistance and force relationship, but then also the type of contact motion that you have. So this is an example for pure copper, which is used in contacts, but not necessarily the best electrical contact material for your contacting interface. But you see that the contact resistance is rather high if you don't have any wipe. And this forces you to, if you want to bring your contact resistance down low, you end up going to very high forces, right? Notice this is in grams, so relative to here, 100 grams, right, is about a Newton. So this puts us, about here on this graph, all right? And then you see with the wiping action, you get, a gross, nearly order of magnitude reduction at the low forces in the contact resistance by utilizing contact motion to reduce contact resistance. Now, I've mentioned a couple times utilization of multiple contacts on a circuit, or redundant or a multiplicity of contact fingers. And you can see here's a model that shows that when you do select design that utilizes redundant fingers or redundant contacts, that they need to be independent spring contacts, right? Because you see if we have some substrate here, and then you have some resistive particle, and then you have your electrical contact, you need to be able to utilize the power of multiple parallel resistance channels to shield yourself from the effects of the high resistance particle. All right, so now if we build, let's call this a sliding contact, and we want to look at noise. So we're going to take this model, and now this model is going to run where your contact moves over the resistance or resistive track. All right, and we're going to have resistance increasing from left to right. And we're going to look at different numbers of fingers. And you see that the green line for one contact finger, all right, that hits some randomly distributed particles, field of particles, that you have a fairly noisy curve. Now, if we add two contacts and you run along the same track of randomly distributed particles, now the noise is reduced because of the parallel resistance. And then the red curve is 5 contacts, and then the white curve is 20 contacts. So you see that there's then some, there's an incredible power to utilizing redundant contacts, and there's some diminishing point of returns where, 20 contacts, unless you're very, very light contact forces, is not necessarily needed or optimized design. When we look at high forces, here's an example of an area where you would use potentially use very high forces in high power contacts, where here's two contacts, and two contacts, as two contacts come together, you have what's called a constriction resistance, and that leads to, at high currents, a blow-off force, right? So change in magnetic fields essentially wants to cause the contacts to separate from each other. And that blow-off force, if you look at the dashed lines, they're representative of that blow-off force, where at currents, say 2000, say on this, for this particular design, at 2000 amps, your blow-off force is 2 newtons. So, and then if you're up at 5000 amps, your blow-off force comes up to about 9 newtons. So these types of attributes, as well as the arcing attributes of the contact, say when they're closing, then start to force you to very high contact forces. So now segueing into a little discussion of now choosing a contact concept and the material properties. Right, so we have certain universal concerns that we try to address. Right, managing debris, any assembly. Even those assembled in a clean room, right? You have to manage and design for how you're going to accommodate debris. Maybe it's debris in assembly, or maybe it's how you're accommodating for debris in use. How's the user interfacing with the component, right? And frequently, can the user actually come into contact with the electrical contacts and then potentially damage them? Then obviously design for manufacturability, and what we see has a large effect on the contact performance is understanding stack-up tolerance. Generally, we recommend trying to iterate towards lower spring rates to be more accommodating for things like stack-up tolerance, and longer, and to achieve that, really longer contacts, thinner material, lower modulus. We'll get into that following. So for the purposes of this discussion, we're utilizing an example of a simple cantilever beam. Right. So first, we're going to need to select some material to start out with. And here's an example of 2 extremes of a materials that are used for electrical contact springs. So not necessarily used as the electrical contact interface, but used as the mechanical spring member. right? So Inconel, higher yield strength, higher modulus. Phos-bronze, so copper alloy, lower modulus, lower yield strength. But really, for most of this discussion, we're only going to be concerned about modulus. One of the reasons is that a lot of electrical contact systems are really defined by strain. So they're strain-driven designs that are not operating on a principle of, okay, well, it's going to be a floating contact that will always be at a certain constant force, right? So if you look at these two materials, their approximate strain to yield is similar. So I'm not going to worry too much until the end about starting to understand the interaction of yield strength, and first start out with what kind of range of modulus, especially because there's a lot of material options that are available in the range of modulus between 16 MSI and 30 MSI. Oh, sorry, I've got it later in GPA. It's like 110 GPA to like 220 GPA. So the simple cantilever beam, right? So we have a beam. It's of a certain cross section, maybe either a diameter of a wire, or it's made from ribbon or strip and has some height and width. All right, it has a certain length, and then it's going to be subjected to some deflection, and it's going to result in some force. Right. So we want to estimate the spring behavior. So the moment of inertia is important. Right, that's going to drive part of our spring behavior. Modulus, which we discussed in the last slide. Right, the length of the beam, and that's going to lead us to some spring rate. Right, so the some force that's the result of some amount of deflection. So this would be, say, newtons per millimeter. Now. Very frequently, then when you go to do calculations, this is frequently represented as either, hey, calculate the force or calculate the deflection from the other spring attributes. But really, we're designing a spring. And the spring rate is critical because we know that sometimes the deflections can be variable. Either that's designed in or that's a stack up of tolerance. So in selection of the mechanical configuration, what's the relationship between the spring rate and the geometrical attributes, right? So what are the stronger levers, if you will, to pull to control this spring rate? Right? So you see that it's linearly proportional to the modulus, say for a rectangular cross section, the modulus and the width of the beam, right? And the length of the beam and the thickness of the beam are going to have the strongest influence on the spring rate. And so typically, if we're trying to have a lower spring rate, right, we try to go to longer designs and thinner materials. And similarly here is the relationship for round cross-section. Okay. So after you make those selections, then there's the concern of now what's the estimation of the maximum stress. So right, the max stress is simply a function of what's the figuring out what's your maximum strain and the modulus of the material. So here we're talking about a fiber stress. So in this beam, as the beam is deflected, the outside fiber of material is in tension, and we want to understand the relationship of how much strain is in that outside fiber, and then what's the resultant stress, right? And sort of from the mechanical standpoint, that's frequently derived by looking at the moment of inertia, the moment and the neutral axis, right? And then as we follow this is the process that's followed in many, say, mechanics texts, where then we reduce this to understand what's the load, the length gives you the moment, and then you get this now, substituting I in for the moment of inertia. I've just added proportionalities because I've taken out some of the factors. But really, if we want to understand how that this almost counterintuitively looks like, well, to minimize the stress, you want to increase the thickness and the width of the beam, which is kind of hidden that these are also in the understanding what the load is, because our deflection, we're looking at a sort of fixed deflection system, right? So really we want to look at then simplifying it and understanding, well, what's the role of the contact geometry in the contact force as well as in the moment of inertia. And so simplifying that out, you see that for the strain, it's related linearly to either the height, or rather the stress, the height or the diameter, depending on if you're dealing with the rectangular or the round cross section, the amount of deflection, and then inversely proportional to the square of the length. And so this really tells us, well, you know what? Reduce, minimize, again, sort of the thickness of the material, and your deflection is essentially going to be largely a factor of what kind of assembly you have, and then the length. So you want to go longer to reduce your stress, and that's a very powerful tool. So one of the reasons we talk about simple cantilever beams is because you always want to start with the simplest design and then iterate to the more complicated. So we have some target gram forces, and we talked about, just rule of thumb, where do you start for a certain type of contact? And then material modulus, and really starting to look at material modulus as a range. What's an optimal min, max type material modulus? Obviously, there's materials that have lower moduli, there's materials that have higher, but these are good starting points, right? And then sort of figure out what the mechanical configuration needs to be. And then for thickness and diameter, I mean, very frequently we see that all of these factors come together to really result in very common types of ranges in material thickness. And so this, and of course this presentation will be provided afterwards, these are good numbers to start with. Thicknesses on the order of say 0.2 millimeters to 0.07 millimeters for low to medium force applications. Then high force applications, some of the materials go as thick as 1 millimeter. And then talking about spring rate, many of these contacts operate between spring rates of like 0.05 newtons per millimeter to 0.1 newtons per millimeter. So now that we've talked some about what the contact system will look like, we start to model the system. Right? And in modeling the system, frequently we start with an FEA. So after we've done some calculations, maybe even some quick hand calculations to get to some approximate beam configurations, very frequently we don't end up with necessarily a simple cantilever beam. This is a little more complicated in that you have a cantilever beam where the two fingers are then joined together by a wider section at the base. Right? And once we model it these days, really then transitioning to a finite element analysis is the next natural step, right? So we look at this contact, and we modeled this contact in two ways to look over a very large range of deflections. So this range of deflections takes us from 0 up to about 2.5 millimeters, and we did two ways. We did an elastoplastic model and an elastic model. And the elastoplastic model shows us that our elastic model is most likely completely invalid after about 1 3/4 millimeter types of deflection. Okay. Other elements of the model that are important to consider: contact position versus working height, contact point of tangency, beam buckling behavior if the contact's moving, and moving in bidirectional, so one way, forward and back, say, and then wear rate versus working height. So an example of contact position height, say this is our contact from the side view, and now we've deflected the contact 1.5 millimeters. So you see now the contact rotates as it's deflected. So choosing contact shape, right, and understanding how that contact shape is going to interface with the mating contact surface as that point of tangency changes, right, and then the contact moves. So what range of contact position do you need to accommodate? If it's an encoder application, what range of positional accuracy do you have to have? And then as we look at wear, if you have a high wear system, which some systems are very high wear, as you wear through the contact, see these gradations represent as the contact height changes as you wear through it, right? The wear face and the angle that the contact is relative to the substrate is going to change. The other thing to note here is that based on contact shape, the height change, all right, with time, it's going to, because wear is a volumetric process, right? The height change will be faster sort of at the initial break-in period, right? Then it will slow down. It slows down as you go to larger and larger sections, right? And then after you get halfway through, then it will accelerate. So after you've built, say, a model that you're happy with and that you think is worthy of going through some characterization and testing, right, we get into characterization. One typical characterization tool used is just simply a cyclic force versus deflection curve, right, where we now, say on a uniaxial tension compression test bed, we have a load cell set up, and we can deflect the contact. Loop 1 brings us up the curve and then down. That results in, because we have very high deflection here, that results in some amount of plastic deformation. So the point where the curve comes back down to 0, and then the gap on extension shows us the amount of plastic deflection. And then we can cycle the curve up again a few times and show now what the force deflection curve looks like after the contact is yielded. So this is an effort to characterize, say, both like the elastic and plastic behavior of the contact. And now we want to compare that to the FEA model. Say, well, at what regime was our FEA model maybe good, and where are improvements needed, right? So this is the idea of, when we utilize an FEA model, do we have a methodology to validate the model and the associated assumptions that we made in generating the model, right? So if the models don't match at all, that tells you, hey, we need to either change our assumptions, utilize a different modeling technique. What's wrong with the test or the characterization method? Here you see that the elastoplastic did an all right job with anticipating the behavior of the part in the first cycle. And then if we shift over the elastic curve then, after the contact's yielded, and will be elastic between 0 deflection and the yield point, the elastic curve is now valid, and the only portions of the elastic curve that are invalid are the points that are above that yield point. So now to characterize more elastic and plastic behavior, we can do a whole stack of these curves. Right. And this brings us to the question of to yield or not to yield. Yielding accommodates very large deflections and deflection ranges. It may also, because the curve starts to flatten out as you start to yield, you may minimize the contact force range in the assembly if you need to accommodate large deflections. But if the contact deflection is going to cycle, you may be fatigue sensitive. If there are separable and swappable contact pairs, so if one assembly isn't going to be mated to the other side of the assembly for its entire life and may see another assembly that's at a different height, that might be dangerous. It may not operate the way you anticipate. All right, and those higher stresses when you yield a contact may also leave you more prone to issues with, say, stress relaxation. So we take this to understand the behavior of yielding and elastic versus plastic behavior of the contact. We take this this cyclic deflection set of cyclic deflection curves, and we generate a couple curves from this. So we have our max force at deflection. We have how much plastic deformation was at each of those cycles. And then we're going to have a reduction in the force at that height, at a couple certain heights after over deflection, to say, well, okay, if we were yielding at any one of these positions, say you cycle up to here, well then if you ended up cycling the contact up to here and then coming back down, what's the gram force if the contact were to be able to go from this height back to this height? So those four curves can be assembled into this graph. And the way we use that is we say, well, onset of plastic deformation is at about 1 millimeter of deflection here. So it's essentially the inflection point of our plastic deflection curve. So we have plastic deflection on the right axis, total deflection at the bottom, and then on the left axis we have the force. Right. So the open boxes we read to the right. Next, if that nominal working height, say, is pretty severe at 1.5 millimeters, all right, the contact is over deflected to 2.5 millimeters. The contact force drops from, so now I'm going to read this orange curve. The contact force is going to drop from 20 gram force to 17 gram force if it gets over deflected and then comes back down to the nominal working height. All right. Now, so this is at 2.5 millimeters here to here. You see, if it were over deflected just a little bit from 1 3/4, you get a much smaller drop in the gram force. Right. Now, what happens if you were to have a very large oscillation in height? So if the minimum working height is 0.6 millimeters and you over deflect to that maximum of 2.5 millimeters, this orange curve here, this orange data point, right, you're going to see that the contact force has dropped to 5 gram force. So, and that's for 2 fingers in this particular design. So you've gone from a contact force at that minimum height that's within sort of the recommended minimum range of the 4 or 5 gram force per contact to something that's now below that and really very borderline from a contact resistance perspective. And so if you looked at this and said, well, you had this, I mean, this is maybe a very wide range of deflections for a contact assembly, but it does say that if you actually had that type of range, that the model suggests and the characterization suggests that the performance of the contact at the 0.6 millimeters is going to be suboptimal, and you'll probably have noise issues. So that's the type of characterization that we'd do ahead of time to say, well, should you even enter into a test cycle? So go through a characterization. If you go through characterization, that can then launch you into your test cycle if you like the results. If not, you iterate back so that The resources, because usually we see in durability testing, the resources and the cost of durability testing is much higher than, say, the cost of characterization. And also the time to characterize is usually shorter than the cost, the time to do durability testing. So that really encompasses the entire process, and if done effectively and pretty efficiently, it leads to a pretty smooth product launch ultimately, and then very high reliability products. This presentation, along with some other tools that we're working on launching at Deringer-Ney, are meant to sort of help the interface with us and our customer base, but also act as tools that you can then use really independent of Deringer-Ney if you wish. We're working on launching shortly an electrical contact design website app that will help you through some certain simple cantilever beam type calculations, and then an application checklist. So this type of tool here, where you have an interactive form that you can fill out, and this either just drives internal DFMEA, or you can actually fill this out and send this over to us and say, hey guys, here's an initial explanation of the product I'm working on. Let's talk about design and manufacturing. And with that, that concludes my talk. Thank you very much for all of your time today.